All right. Welcome, everyone. Thanks for coming to such a niche topic on the very last slot of the day. Hopefully, you'll get some good takeaways from this talk. So this talk is about how we're trying to build and compose the VEX Kubernetes feed to talk about so that we can communicate the vulnerability impact to our end users. My name is Adolfo García, or Puerco. That's my usual pig. If you see that on the internet, it's me. So I am a software engineer in a super new startup called Carabiner Systems. But more importantly, for this talk, I am one of the tech leads on Kubernetes SIG Release with the release engineering team. And I am also one of the technical leads in the OpenVEX on the Open Source Security Foundation, which is a sister of the CNCF. So you can think of me being here on this stage wearing those two hats for the day. So here's a quick rundown of what I'll try to touch on today, because it's a lot to pack into half an hour. So I'll do like a super quick intro on what VEX is. We're also going to show how we're thinking on VEXing the Kubernetes project and the challenges of doing that for such a large project and organization, and finally show you a couple of new tools that we're working on to make this a reality. And hopefully, if the internet works, because it was failing very bad half an hour ago, we'll get to the demo. So first up, VEX. So what is VEX? If you had to define VEX, you can think of VEX as a system of documents that get chronologically ordered that communicate the impact that a vulnerability has on a piece of software. In other words, if there's a CVE, does it affect me or not? And that's a channel of communication between you and your users and downstream tools and other processes that enable you to make assessments on the exploitation capability, like the exploitation possibility of that vulnerability. So to go a little bit more into detail, let's assume that you have a container image. In VEX slang, this is called the product. So when you have a container image, you will usually point your security scanners at the image. And over time, you start seeing that CVEs start showing up. This is normal and completely expected. And most of the time, it is because your container image has dependencies, and new vulnerabilities get reported on those projects every time. So most of the time, the vulnerabilities will come from your components, which in container images, you have roughly two kinds. One is the operating system dependencies in the image, and the other kind is the language dependencies that you use for your software project. Scanners will find those dependencies, compare them against security databases, and give you a report on whether those are found in your components. Now, with VEX, what happens is that you have your piece of software, and when you have your released artifacts, you supply the scanners. You will also issue a VEX document that pairs together a bunch of information, which we'll touch in a little bit. And then when you scan, the VEX document gets fed to the scanners and other processes that understand it. And then they will still find those vulnerabilities in your artifacts, in your container image, but they can understand that they do not affect you, and then may choose to suppress them from the output. So that's kind of the really core way of how VEX works. A VEX document has a number of statements, and each statement pairs together your software product, which is, in this case, the container image, the component where the vulnerability was found, and vulnerability itself, and that gets paired with a VEX status label. There are 4 labels. One is under investigation, which is a way of informing and acknowledging to your end users that you know that there's a vulnerability present, but you're working to understand the impact it has. There's affected once you assess that the vulnerability affects you. Not affected, which is kind of the most widely used VEX status. And fixed, which is once you understand how the data flows, It's a kind of a niche flag. It's difficult to use correctly, but it was there just added for completeness of the flags. There are 4 VEX 4 flavors, we call them, because VEX was defined by a community group hosted under CISA, the Cyber Infrastructure Security Agency in the US. They facilitated a community group that works on VEX across both here in Europe and in collaboration between people here in Europe and the US, and also a lot of people from Japan. And then, so there's a VEX flavor in CSAF, the Common Security Advisory Framework. It makes sense to have it there because once you publish a software advisory, you can also issue VEX in the same format. There's one flavor of VEX in both of the SBOM formats, one in Stacklok, one in SPDX, and of course the one that we care most about, OpenVEX, which is the flavor of VEX that we are developing in the OpenSF. OpenVEX, contrary to the other ones, is intended to be VEX and VEX only. It's supposed to be super lightweight and embeddable in other formats, such as attestations, which we're going to see in a little bit. But you may be thinking, well, why should I care about all of this VEX stuff? Well, it's important, and we think it's about to become a little bit more important because of the CRA that's coming up in Europe. So if you look carefully at the text of the CRA, it has some mentions about vulnerability management like this, like you cannot put a software product on the market if it has vulnerabilities that can be exploited. And sometimes those vulnerabilities, for example, if upgrading a dependency is like a really costly solution and the vulnerability doesn't affect you, you can choose to VEX it, and you will technically, I'm not a lawyer, but we think that this will satisfy this requirement. Or also, there may be other cases where you issue your own patches and scanners are issuing false positives, and then you may want to VEX them as well. Or maybe sometimes, as is the case of Kubernetes, the security advisory doesn't have enough resolution, so some artifacts appear as vulnerable when they are not, and so on. Here are other instances of vulnerability management that VEX can address. So, for example, you need to provide disclose information about fixed vulnerabilities. VEX has a channel for that. The impact of the vulnerabilities. VEX is the way, it's the reason that VEX was designed, and it has fields so that you can publish that information. And as well, about remediations that you may use to remediate those vulnerabilities. Now, let's talk a little bit about the challenges of VEXing Kubernetes. So VEXing is not easy because it requires either information from a tool that you can trust or information from a person that you can trust. And in the case of Kubernetes, it's such a large project with so many sub-projects and code areas that it's hard to understand how to VEX properly. So there are issues around who can issue those VEXes. So who can you trust? Who has the specific knowledge in depth of the code base so that they can issue the VEX statements. There's also an issue around also authorization. So if you're someone who's authorized to issue those VEXes, how can we let you do that in a secure fashion? Then there's the aspect of publishing. Where do I put these documents? Then there's the question of data sources. We'll see in a little bit how we're structuring the feed, because there are many ways, there are many sources where VEX data can be originated, such as our own CVE feed, but also the maintainer assessments, output from tools, and other sources may be possible as well. And then finally, the whole publishing. So how do I publish? Where do I put them? How do I manage the lifecycle and all of that? Obviously, this is a multi-SIG network effort. So not only we in SIG Release are handling this problem, we have ongoing conversations with SIG Security, so we're teaming up with them and with the SRC to ensure that we can together manage the project. So after some discussions, we came what we call the big Kubernetes VEX plan. And the goal of the big Kubernetes VEX plan is to have a VEX feed. And since I'm also one of the people working on VEX itself, it's really important that we are very strict on what we want VEX to do. So we were thinking, so how does the perfect and most complete VEX possible look like for Kubernetes? So the big VEX Kubernetes plan, we are planning on having one feed that is itself a mix of three different fixes, the three different feeds. So the first one is VEX about vulnerabilities that show up in the Kubernetes dependencies. That by itself is in reality two feeds that are mixed into one. One, SIG security runs periodical scans, so go vuln check on the Kubernetes code. And now the idea is that we are capturing that output. So go vuln check is the analyzer from the Go project that gives you the reachability of vulnerabilities. So if your code has a vulnerability, go vuln check can analyze using the compiler if the vulnerability is actually reachable in your code. It has native OpenVex support, so you can just pass it the flag format OpenVex, and it'll give you an OpenVex document. And finally, well, so that's one. The other, so this is coming from Go vuln check. The other one is a VEX from generated from maintainer assessments. So assessments, the true, the most senior maintainers of the project, can, if there's a vulnerability in the areas of their code, they can generate an assessment that says, OK, even though there's a vulnerability in this Go module, we don't think it affects the project, and sign it, and then send it. So that's the first part. This is where we're at. So we have tooling to do this already. And I'll show you the tools in a little bit. They're general purpose tools, so it's not only for Kubernetes. So if you want to issue VEX in your organization, you can use the projects we're going to present. The second one is the Kubernetes VEX feed generated from the Kubernetes advisories. So when you publish an advisory for Kubernetes, which is on numbering authority, so if Kubernetes, the project has the authority to issue its own CVEs, we can also generate a VEX feed to complement the advisories. The way to think about it is like it's the negative of the advisory. You issue an advisory and says, OK, the kubelet version whatever is affected by this new CVE. But here's all the other VEXes that tell you that the other artifacts are not. So the kubectl binary is not affected, and so on. And finally, so in the way we're doing this is that we have a plan, and this is the next stage in the project. We have a plan to rewrite the Kubernetes VEX feed in the OSV format, which is another vulnerability format that is incubating in the OpenSF. And the idea would be to start from OSV, write the advisories in OSV early, and from there we can generate the other different formats that we need to be able to generate the project vulnerability feed. So one is the CVE feed that gets published, where scanners find the information of Kubernetes, the JSON that gets sent to the CVE database, and also the information that we capture and publish in the release notes every time there's a security release there's security information in one of the releases. So once we have those, we can feed it into the VEX processor and generate another one of the VEX feeds. And finally, and this is, well, we still not need to discuss a little bit more of this, is the CVE information that gets picked up from our container-based images. Usually, our container-based images, some of them are heavy, have a lot of dependencies, so a lot of CVEs sometimes show up. So we're thinking what to do there. And then once we have the VEX feed, we can take those VEX statements and publish them somewhere. And somewhere can have a number of possibilities. So we have the Kubernetes. We could build like a Kubernetes VEX feed. That's one possibility. We can push them to the registry with the images so that scanners can find them. Or Aquise also has this project called VEXSUB, where they are trying to host VEX information for a number of open source projects. All right. OK. So to tackle the challenges of issuing VEX in the organization, we wrote a new tool called VEXflow. And VEXflow is a tool that gives you a ChatOps interface in GitHub issues so that you can handle the VEX lifecycle. And this is how it works. So you take a repository, and then VEXflow will constantly scan the repository over and over and over, and at some point, it will pick up a vulnerability in your code. And once it finds it, it goes to GitHub, and it opens an issue with triage instructions. And these triage instructions contain information on how the maintainers, OK, it's below that, how the maintainers can interact with it so that they can either ignore the issue a VEX statement, or just issue another one of the VEX statements. So once a maintainer, so one possibility is that you just leave it there, don't do anything, and we're thinking maybe it'll just auto-close after a while. Or the other one is that one of the maintainers can come in and do an assessment, say, OK, this is, yes, affecting us or not affecting us. That gets captured into a VEX statement. And to solve the issue of who can VEX, this tool natively supports the owner's file that the Kubernetes project uses. So you can define the maintainers in the owner's file, and the plan is to support like aliases and everything. So that's when you interact with the issue, it'll look to see if you're there, and also new names that need to issue VEXs can be authorized via pull request because they get captured there. So once an assessment gets made, we capture the assessment, we capture the comment, convert it into an open VEX statement, sign it with SIG store, and then we push it to the GitHub attestation store. It's a new feature, well, rather more or less new. I think it's like a year old, that any project can generate attestations and push it so it gets stored in the GitHub attestation store. And then the issue closes. So this is the flow of how it works. So scan periodically, vulnerability, opens the issue, you get capture the assessment, and then it goes. So so if you remember the initial, the VEX feeds of Kubernetes, the first two, this is one of those. And the other is the Go vuln check. So we have those two feeds. One is the VEX data that comes from this process, and the other is the automated flow from Go vuln check. So this is a clone of a VEX lab I'm working on. So this is the first demo is going to be about this critical piece of technology that I called, I call this project the Insult Connector 2000. So the Insult Connector 2000 is a piece of software that implements in Go a proxy connector, but it never connects. Its only purpose in life is if you try to connect, it'll give you back an insult. So I hope they're not too spicy for the audience here. So for example, I try it. Oh, no, I won't connect. No, I won't connect. So it will never connect. But in reality, well, obviously, the purpose of this code is to demo the vulnerabilities. So you have two vulnerabilities in this code. Here, I'm importing a module that will pull in one vulnerability, and by using this version of the version of XNet that I'm using, it'll also give me another one. So if I scan this project, it shows me two vulnerabilities. So the OSV scanner is like pairs with Go vuln check and lets you know that one is supposedly exploitable and the other is not. Now the first one is theoretically exploitable, but since the only purpose of the insult connector is to give you an insult, it will never connect to the net, so it cannot be triggered, or you're safe from that one. So over here in the project, so the way VEXflow works is that you give it a repository where it will open and handle all of the issues in metadata that it generates, which is this one. So I'm setting it up for this one. So the problem with, so let me go back quickly to the slides. All right, so now I'm running out of time, so I'll just do the demo. Okay, so let's say that the authors of the install connector wanted to generate to make the project compliant with the CRA policies that they require you not to have any vulnerabilities. So the project release is fairly straightforward. You have a bunch of Go files, build a binary, and push it out. So now the way that the project attempts to comply with the CRA regulation is that, well, you implement a process where you scan your project, and if there is a vulnerability, you block it, and then it will stop the release if anything gets found. So using VEX-Flow, we can do that. So the first one is, so this is supposed to be running on a cron or also as a GitHub app, but I have the actions stopped, not the crons running, so that we can go and slowly see how it works. So I'll attempt to run the VEX-Flow job so that it updates the vulnerabilities in the project. Now, internally, we link OSV, the scanner. So it's importing it as a module and running it natively, but it also has an example in the code base where you can use it to basically shell out to other scanners if you prefer another one. All right, so this run, hopefully, yeah. So it ran, and it went and scanned the code base, and it found those two vulnerabilities. So the first one is, the first one here, you'll see that it's the one from the net module. So this one is not exploitable, as it is exploitable from the point of view of the scanners and Go vulncheck, but since the program never connects to the net, so it's not really exploitable. So what we do here is that we issue a VEX statement here. This project never connects to the net. So in VEX, when you issue a non-exploitable, not affected statement, you also add a justification, which is the second part of the / command there. So it's not affected. Why? Because the vulnerable code cannot be controlled by the adversary. And then you can also add a human statement below, which is what I'm putting there. What I put in the comment, it's going to get captured, written into the VEX statement, and then published as a VEX statement. So that's the first one. So in a little bit, the bot should reply that it already issued an attestation. So if I go in this project to the attestation store here, you'll see that I already have an attestation, and the attestation type is OpenVex, and then unfortunately the UI doesn't show you a lot, but it's there. And now, so that's one. That's part of that's one of the others. Now to simulate the way we're doing the VEX statements, I'm going to run the other one with Go vulncheck. So this workflow runs Go vulncheck, and the only difference between Go vulncheck is that it will give you like an unsigned document, but this action will actually generate the attestation, sign it, and push it to the registry. So we're probably going to run out of time, but I'm going to show you here. OK, just let it finish. So inside of this, it's running the Go vulncheck. It takes a while because Go vulncheck, it's compiling it from source. So once it runs it, it'll capture it. And then, well, once you have all of those attestations, the final command is, so you run VEX flow with this assemble subcommand, and what that subcommand does is that it goes, scans your repository, fetches out all of the vulnerabilities that are still present, picks up all of the VEX statements that are available for the branch. Any that are not in a vulnerability get discarded, and then it assembles a full document with the CV data that you just generated. This is missing the second one, but you get the idea. So I'm not going to go deeper into the release process because I'm running out of time. And yeah, so once you have those VEXes, the policy of no vulnerabilities gets done, and all of the vulnerabilities are suppressed once the scanner picks those documents up. And yeah, so almost at time. So this is kind of the gist of it. So here's the data about the project. So we need to have a conversation on where the VEX flow tool is going to land. There's on one side, we could have it on Kubernetes, or we could donate it to OpenVEX. We have to have that conversation. And then, if you're interested in joining the VEX talks, we have meetings every other Monday, or join the SIG Release meetings where we periodically do updates on this sub-project. And yeah, thank you.